Hello, everyone. Thank you for coming. My name is Martin. I'll today talk about intelligent distributed system optimization. So I'll talk about how we can use machine learning to optimize our large-scale distributed systems. If you're interested in distributed systems, we're working on a book with some of my colleagues, and we present many of the typical things you have to solve in distributed systems, like consistency, reliability, and present it on examples from practice. So if you're interested, have a look. As a motivation, which one of these two code snippets do you think performs better? Which one is faster? The fold left on the left or the while loop on the right? It's probably the while loop, but I didn't really measure it. It also throws an index out of bounds exception. So I guess what I'm trying to say is optimizations are difficult, and we'll see quite a few examples where you have to really do some sort of trade-off and choose what you want. In this case, is it readability or is it performance? But we won't talk about any of that, don't worry. We'll talk about optimizations at a different level. We'll talk about optimizations not at the code level, but at the level of the whole system. We'll talk about how you can look at the system from a statistical point of view and try to improve it in certain direction. And when optimizing a system, we don't necessarily have to talk about performance. We can also look at things like cost, reliability, uptime, and many other statistics, pretty much anything you can measure in your system. So I'll just quickly go through some of the techniques used in the state-of-the-art systems like Apache Spark used for optimizations, and then I'll transition into the area of machine learning and how that can be used. I apologize in advance, I have a couple of TensorFlow slides, so if you don't know Python or TensorFlow, don't worry, I'll try to go through it so quickly that you won't have time to be confused. So most of these systems, like Apache Spark, good example are relational databases, SystemML, TensorFlow, FreeMonad. Most of these systems, they apply automated optimization. So you write code, but that's not necessarily the code that actually runs. So I'll go through some of the optimization steps. The first one is logical optimizations. So when you write code in Apache Spark, the code on the left, it's nice SQL-like syntax, very high level, but it does not immediately execute. It translates into that computation graph on the right. It's really just one-to-one translation, the exact same thing. So we have a couple of filters, then we join two tables together, do some more filters and projections, and at the end we group by the result. But what Spark does, it actually applies semantic preserving rewrite. So it tries to simplify the graph so it executes more quickly. It, for example, moves projections to be executed as soon as possible in the computation. So we project ID and username before the join, and then we project username immediately after the join, because we don't need ID anymore anywhere else in the computation. So that allows us to drop some of the columns that are no longer needed and therefore avoid copying data around. Another typical optimization in relational databases or in Apache Spark is pushing filters through projections. So we take the filter and we try to execute it as soon as possible, where eligible. Because that, again, allows us to get rid of an amount of data. It can be a huge amount of data that we just get rid of, and we don't then have to use it in the join, and therefore the computation is faster. So that's the first step. And the output of this logical optimization phase goes into the physical optimization phase. Databricks very recently announced a cost-based optimizer. So what that does is it creates possible physical execution plans and then uses cost-based optimizer to pick the best one. The best one that has the highest probability of executing as quickly as possible. And the way it does it is it gathers statistics about the data. So relational databases usually do tracing queries with small amount of data, and they try to understand what the data's characteristics are. So, what each column type is, what are the most common values, what is the average value, and just tries to understand statistics of the data and then estimate the amount of data after each of those operations. By doing that, the optimizer knows how much data roughly will be available for the join, and it can choose the best implementation of the join. So if one of the sides of the join is small enough, it chooses a broadcast join, because that's very efficient when broadcasting some just small amount of data. But if both of the sides are quite large, the optimizer chooses to use shuffle join, because that's more efficient in that case. But Spark takes it even further. It often acts as a compiler. So it does these optimizations, and then instead of interpreting that high-level computation graph, it emits a low-level Java code. And the Java code is compiled and only then executed. The reason why it's doing it is because interpreting a large or high-level Java code actually results in a lot of virtual function calls and virtual dispatch, which is expensive. And emitting low-level Java code allows you to optimize for data locality, for having your data in registers. You can also use advanced CPU features like pipelining and many other things that, again, improve the execution time. So that's Apache Spark and relational databases and other similar systems. But when you're building your own system, which is not based on Spark, if you're building a general microservice architecture, you usually don't have that automation available. You have to do all of that yourself. But we usually actually do that, all of that ourselves, but we have to do it manually. We have no algebra to help us. So essentially, when building a system, we still look at the low-level optimizations. We optimize the code. We optimize what data structures we actually use. We optimize the object allocation, garbage collection. But at the same time, we apply optimizations at a higher level, the logical and physical optimizations. So we apply things like caching, batching. We do things like load balancing. And all of these things are very similar to what Spark is actually doing, but we have to do it manually. We have no algebra to help us. Good, so let's look into how machine learning can actually be used for optimization of distributed systems. Machine learning is becoming increasingly popular. These days, it's used in many commercial products for many things like stock market predictions, object recognition, self-driving cars even. So many interesting use cases. Essentially, when you go to an online shop, to a website, they quite often track everything you do. They track your actions, they track your clicks, they track which pages you visit, what you search for. And by doing that, they can optimize the system, is one thing. And the other thing is they can actually optimize the experience for you as a user, because they know what you are interested in, and therefore they can serve you things that you're actually going to be interested in the future. So we'll do something similar, but with a distributed system. We'll talk about how we can gather a lot of data about the system and its behavior, and then we'll use machine learning to try to improve the system in certain direction, which can be either performance, cost, number of failures, or something else. So to be able to do that, first we need observability. These days, observability is usually defined as the combination of logs, metrics, and traces, at least, because that gives you visibility into what the system is doing. If you don't have observability, you don't know what the system is doing at all, and you can't progress to the next steps. Next steps are analytics and understanding the system, and only if you understand the system and understand its behavior, you can start performing some actions. Because if you're not measuring and understanding, you can make changes in the system, but you don't know if they lead to an improvement or not. So those are the first steps you actually have to take. And only then the system becomes really reactive, because you know what you're doing. You're reacting to situation and improving the system. And in many cases, or in some cases at least, you can actually try to predict the future. And instead of reacting to situation, you can try to predict it and act slightly in advance. So let's very quickly cover some of the data sources for our machine learning models and for our distributed system. Metrics and monitoring is first one. I'm assuming most of you have built a production-ready system, and anyone who's done that just understands the importance of good monitoring. So monitoring gives you an overview of the health of the system, what the system is doing as the whole. You can measure things like the JVM statistics. You can measure the number of requests, the average response time, and many of these things. This is an example using Prometheus, where we gather statistics about latency of our request and response. Especially with the modern time series databases like Prometheus, you can do aggregate queries and therefore learn a lot about your system as a whole. But it's not as useful for understanding single user behavior, but that's why we have logs. So logs should absolutely have context. So logs should give you context about the user who's part of that query, about the service where it's executed, about any other data, like where the log was executed and so on. Absolutely do not do this. Don't create the structure yourself. With languages like Scala and others, you can build a decent DSL that injects or does all of this for you, and you can simplify it a lot. But usually the output these days is recommended to be JSON because it's readable. It integrates really well with a lot of tools, and logs allow you to, in many cases, debug a query for single user. So you can look at what's happening for that one user and see where some errors happened. It, however, is not very good at tracing or looking at the system as a whole. Because if you look at the whole system as a human, it's usually gigabytes or terabytes of data. And it really feels more like this. It's really difficult to find anything in it. But that's where machine learning can actually help a little bit, because it can try to find correlations in the data. Like, what is the most common failure? If there's a failure, is it correlated with some other failure that happened at around the same time? Or which version of the service has the most failures? And many other interesting things are hidden in the data, but they're just not accessible for a human. And the last part of observability is traces. Trace essentially means we create a trace ID, a unique identifier when the query starts, and we carry that identifier all the way along with the query. So any log or any event that happens as part of that request has the trace ID associated with it. It's really useful because it gives you the before and after relationship, and also you can track lineage of each event. So if something happens, you can track it back, and you can track the sequence of events that led to that failure or success, and you can actually see and you can reproduce it if you want. Again, gives you really good insight into what one user is doing, but there's a lot of information hidden that a human cannot easily extract, like, let's say, an average time a certain function takes to execute. So most of the things I'll talk about today, they are extremely useful, especially when talking about economies of scale. If you have an online shop with running on one machine and the system goes down for a couple of hours, that's probably an important, huge hit for your business. It probably will cost you a lot of your income. But the problem is much more amplified if you have dozens or hundreds or thousands of computers or machines. Because then a failure, usually for a couple of hours, can cost the business a couple $100 million. And there have been cases like this even in recent years. On the other hand, the other example is, at this scale, if you optimize your system a little bit, it can have a huge impact. Google was able to decrease their electricity use in their data centers using machine learning by around 15%. So if you decrease your household bill, household electricity bill, by around 15%, it's a couple of dollars, so that's great. But for Google's data centers, 15% resulted in savings of around hundreds of millions of dollars a year, just because of the scale of their data centers. So the machine learning optimizations we'll talk about, they're not about finding perfection of the system. They're about finding the perfect balance in the system. It's about balancing all the attributes of the system, like cost, reliability, performance, and others. This is a quote from the Google Site Reliability Engineering book. You should align the risk taken by a service with the risk the business is willing to bear. So it's not about aiming for perfection in the system. And sometimes it's a business decision that you're not going to implement certain feature. So if there's a risk that your system may be unavailable for a few hundred users every 5 years, it may not be worth implementing a fix if it's a huge amount of effort, but you may instead choose to just live with that, and if it actually happens, then accept the costs. But the important point is this has to be an explicit decision. Has to be an explicit decision by the business. So you have to evaluate that risk and have a chat inside your business and make sure that that's actually acceptable. You can't just have a system full of holes, and if one of those failures happens and you don't know about it, but you'll pretend like we actually wanted that, and the business will be fine with it, they probably won't be fine with it. So you should still absolutely do all the good things in distributed systems, like build consistency correctly and verify it works, and build reliability into your system, and worry about delivery guarantees. All that is absolutely necessary, but sometimes you have to make the decision not to implement something perfectly. So some of the problems commonly solved by machine learning in distributed systems include node assignment. So most companies I've seen, they assign computation or services or applications to their available infrastructure in quite a random way. So it's usually like one container or one application per physical machine. And the blue circle is a database, so obviously it needs a bigger machine. But there's usually no evidence behind that assignment. And also, the performance or the characteristics can even vary depending on the workload. So this is Apache Spark, the same system, but running two different tasks. The one on the left is matrix multiplication, which is a network-bound problem, and therefore running it on one single large machine is more performant. On the other hand, QR factorization is memory bandwidth-bound problem, and therefore having multiple smaller boxes or smaller machines results in better performance. But there's another aspect, which is cost. You also want to find the one that's the best cost performance balance for your organization. So there are many systems that are trying to solve this problem, some of them using machine learning. Many of the resource managers and cluster schedulers are actually trying to solve it. It's a really difficult problem because you're essentially given a pool of resources and you're trying to find the best possible combination of your application placement on those nodes. Especially if you're in a cloud environment or any other environment, each additional machine costs you money. So you're trying to find the perfect balance in that case. The same goes with serverless. Serverless is this concept where, and actually a really popular concept, where you don't deploy your applications to physical machines. You just write functions. And then you give that function to your cloud provider or your serverless provider, and they're responsible for executing that function when it's triggered, so when you want to trigger it. And then you only pay for the execution time. So you don't pay for resources that you actually don't use. You always only pay when your function is executing. This is really useful. Allows you not to worry about the infrastructure and scaling up and scaling down and all these things. But you still have to make some choices, like the size of your function. You can assign 192 megabytes of memory to one of your functions, 1,024 megabytes of memory to another function. And the cost then differs, and obviously the performance differs. So if you have hundreds of functions, how do you find the best possible combination of these sizes or the instance sizes? It's again an optimization problem, and it can also vary depending on the time of the day or some other attributes. So it's another interesting area where machine learning can be used to optimize this for you and find the perfect balance. Another common use case is automated scaling. Many systems these days scale automatically quite, you don't really have to worry about it too much, but they usually they set a threshold, like if the system reaches 80% of memory use or CPU use, we'll add a couple of nodes. But the question is, what's the threshold, why, and how many nodes do you add? Usually, again, this is chosen quite randomly by most companies I've seen. But you can, again, find the perfect combination of these parameters using optimization techniques. And in ideal case, you can try to predict scaling up in advance. This is really useful, especially if you have spikes in your performance. So if your performance just increases rapidly in a short period of time, even the most modern systems usually take at least a couple of minutes to be able to scale up. So we can look potentially at the data. And if there are some patterns, we should be able to find that pattern and scale slightly in advance. It sounds complicated, but in some cases it may actually be quite straightforward, such as if a huge number of users log in, you may expect them to hit your service in the next couple of minutes. The next use case, and I'll spend a little bit more time here, is configuration. So most systems have a huge number of possible configuration properties. Most systems really have like dozens, hundreds, or more of configuration properties. And most companies I've seen, they usually set random values. Well, some configuration values, you really know what is the correct setting. But quite often you don't really know, so you set a random value or leave the default, and then promise to get back to it later. Sometimes you do actually go back to it later during performance testing, but at least most people I've seen, they just tune a couple of those properties. They don't really tune all of them. Do you do the same thing, or do you have a better approach for optimization? Cool. So I'll talk about this example, which is an Apache Spark job. It's a very simple machine learning pipeline. It reads data from a file, then splits the data into two data sets. It's a training and testing data set. Then it trains a machine learning model, in this case a multi-layer perceptron, so a very simple example of a neural network. And when the model is trained, it tests it on a different, or validates its performance on a different data set, on data that it has not seen before. And this is a very common machine learning pipeline, very simplified one. This is the usual flow. But a couple of things to notice. One, we're setting some parameters here. We're setting some layers. We have numbers 4, 5, 4, 3. Why? Why do we have those numbers? We're also setting the block size, the seeds, and max iterations. These are also hard-coded values. Why did we choose these values? And at the same time, Spark has a lot of configuration properties. This is just a small subset of them. This is around 20 of them, but there's many, many more. How do we set these correctly for our Spark job to run as efficient as possible? And also, we want to do the same for the model parameter and hyperparameter tuning, but I won't cover that too much because that's a really interesting area of machine learning called meta-learning or learning to learn, an interesting step towards general artificial intelligence, if the system can learn how to learn more efficiently. But essentially, let's talk about the configuration properties. We have 20 of them, and just based on the combination of these configuration values, the runtime of that Spark job can differ quite significantly. It varies from around 10 seconds to up to 90 seconds, just based on the configuration, and the code stays exactly the same. So how do we choose? How do we find the combination that actually results in the lowest possible runtime? We could try to do brute force search and just try all possible combinations. But if you consider we have 20 configuration values, each of them can have just five possible values, and the runtime of one of these trials is around 20 seconds, it will take around 60 million years to try all possible combinations. So we're used to release new versions of our system a bit more often than that, although not always. But it's a trivially parallelizable problem. So what we could do is we could run the problem or parts of it on, let's say, 10,000 machines at the same time. So that would improve it because it would only take 6,000 years. Still not perfect. And also the cost would probably be higher because I'm assuming the cost of computation will go down over the next 10,000 years or so. So this is clearly not a solution. So we want to be more intelligent about how we actually do this. And one option, probably the most used option in machine learning, is called supervised learning. So supervised learning is about having labeled data. So we just run a couple of random trials, gather the data. In our case, the features are the combination or a vector of all these 20 configuration values, and the label is the resulting runtime. And the goal of supervised learning is to look at the data and try to understand the relationship between features and label. So we usually feed a lot of these training data, labeled data, to our machine learning, to the algorithm, and train the model, and it then represents the function from features to label, and then we can give it a feature vector that it has not seen before, and it should be able to predict the correct label. It's a very, very simple concept. But let's look at how it works with just a one-dimensional space. So if our only dimension is broadcast block size, the only parameter that we can set, and we want to see how the time changes or the runtime changes based on just that one parameter, and run 5 different trials, we can see there's probably some sort of function that we can represent. So linear regression probably is not the best fit and does not represent that function really well. But even using something simple like polynomial gives us a good understanding of what the function looks like. And then we can look for the minimum of that function, and that's the parameter that we should, or the value that we should actually choose for our job. And the same thing works in a multidimensional space. Here we have 2 configuration parameters. We have the number of executed cores and broadcast block size. And we can again see, although this function is no longer represented by a line or something simpler, but it's a surface, but it still has a minimum. And finding that minimum, we could again try all possible combinations, which is expensive, or we can use some intelligent way to find the minimum, an optimization algorithm like gradient descent. So let's look at how this code would look like in TensorFlow. We would define a neural network. Good thing about TensorFlow is it really nicely represents the computation. It's very close to the mathematical representation. So the input is x. That's the feature vector, the feature vector with 20 features. And we define weights, which is essentially just a matrix of numbers. And biases, which is a vector. And then we perform this computation, and the result is called hidden 1. We take the input vector, multiply it by the matrix of weights at the bias vector, and then run it through a ReLU function. It gives us an output, and we use that as an input to the second layer of the neural network. The second layer is exactly the same. The input just is not the input to the network, but it's the output of the previous layer of the network. And we do the same in the third layer of the network. Again, we take the output of the second layer, use it as an input to the third layer, multiply by weights, by some matrix of numbers, add biases, and produce an output. In this case, the output is just a single number, and that number represents the model's view of what is the correct label for the input data. So this neural network's goal is to really just represent the function from features to labels. And then we define the actual computation, the optimization algorithm that improves or trains that neural network. So X are the input values, Y is the neural network, Y with underscore are the correct labels. And then we define how we represent an error. So the output of the neural network, we compare it with the correct label, and if it's not the same, we compute some sort of error. And using the gradient descent optimizer, we propagate that error back to the network. And we do that in a cycle for a couple of times on the data we have available in batches. And the goal essentially is to propagate that error, so the difference between the network's predictions and the correct label back to the network and update the weights, update those matrices and biases, and update them in a way that actually represents the problem in the best possible way. And eventually, after training for a while, the neural network should reduce the error and then be able to represent that one function really well. So that solves our problem. By doing this, if we have the training data, we can solve the optimization problem and find the best combination of our configuration properties in probably around minutes. So problem solved, right? But what problem did we actually solve? We solved the problem where, given a lot of data that we already had, we found the best combination that produces the shortest possible runtime for this particular Spark job. But what if the Spark job changes? What if we use a different machine learning algorithm? What if we change the code a little bit? Also, how do we get the data? To get the data, we had to run a lot of iterations of that algorithm anyway with tracing data or some sample data to produce the labeled data. But I think if we just took the best result out of those random runs, we would be really, really close to the best possible combination anyway, so we wouldn't have to do any of that. So what can we do about it? One option would be to feed the Spark input graph or the Spark computation graph as an input to this algorithm. That could make it potentially general. It's a really difficult thing to do. And the other problem, probably the biggest problem, is where do we get the data? So there are some interesting ways how we can do it, including generative models, synthesizing the data. But we'll talk about a different use case, which is unsupervised learning. Unsupervised learning gives us the same or similar results without having the data at all. And let's talk about a general case. So the previous one was very specific to Apache Spark and one particular job. But let's look at a general case. Please don't try to find any meaning in this picture. It's really just random to show it's complex. So we have an Akka HTTP that publishes some messages to Kafka, then Akka cluster that reads from Kafka or subscribes to Kafka and has a dynamo as its event source backend. It also sometimes triggers a Lambda function because why not? Akka HTTP also fronts a load balancer, and the load balancer sends messages to another microservice that uses a Redis cache and a Cockroach DB backend. So the difference in this system is we, again, don't have any algebra to help us. In Spark, when we run different jobs, they have something in common. But here we don't really have anything. It's a very general system, and each of these subsystems are very different. Each of them scales differently. Each of them has different configuration values. Each of them behaves differently under load, has different errors. So very, very general system. Also, it's long running. It's not the Spark job. We could run it with some sample data, which only took around 20 seconds. But this is a long-running system. Systems like these usually run them once, and then they're around forever. So how do we gather the data? We could potentially run like a performance test with a subset or a sample of data for a couple of minutes, but one that's really expensive. And also, the system evolves over time. So we deploy new versions. We change the code. We change the configuration. We can change how the communication patterns even. So we would have to do this for every version of the system to stay up to date with our machine learning model or our description. Also, there's a large number of variables, like configuration values. Each of these systems has their own, and many of them are also unknown. Like there may be some libraries that Kafka is using, but you don't even know about them, and you don't even know that you can set those values. There's also many possible actions. You can add Kafka nodes. You can maybe change configuration of Akka HTTP. There's a lot of things you can do. And the reward is temporal, meaning that if you make a change, you don't necessarily know if that change leads to an improvement or not until after a period of time. So it may take minutes or hours or even longer to know that the change you made was actually a good idea. So we'll talk about reinforcement learning, which is one of the ways how you can actually try to solve this problem. I assume most of you have seen some of the usages of reinforcement learning. A good example was the Google's reinforcement learning agent that was able to beat the best Go player in the world. And was able to do it without any data, without any historical games, or even playing with people. It just learned how to represent that problem and find the best possible solution to the Go game itself. Other use cases include, was this company, a startup acquired later by Google, that taught or created an agent that learned how to play any Atari game. Self-driving cars are another use case of this. So it's becoming really, really popular over last couple of years. And the way this works, compared to supervised learning, we don't have any data, but the agent learns by trial and error. So it tries to behave in an environment, and depending on its actions, it receives a reward. And the reward is based on the problem it's actually solving. So the agent is in an environment and sees a certain state of the environment, and it takes an action. And the action results in two things. One is the new state, so it moves somehow in that environment, and also a reward. Just imagine the game of Super Mario. I'm sure you've seen Super Mario. You have this agent that can either go left, go right, or jump. And if it runs into an enemy and dies or jumps into a hole, it won't receive a reward. But if it does something good, like reaches the end of the level, it receives a reward. So by doing this, it eventually learns how to behave in that environment and learns how to perform really well and increase the reward over time and therefore reach the end of the level every time. The way this is usually implemented is by, the simplest possible case is to just have a matrix that represents the agent's behavior or its intelligence. And it performs an action, receives a reward, and it has a matrix of all possible combinations of states and actions in those states. And it looks at that matrix and tries to pick the action with the highest probability of yielding a reward in that state. And it does that, then it compares the reward with the expected reward with the reward it actually receives and tries to update that matrix to, again, represent that problem a little bit better. And the equation down at the very bottom is called Bellman equation. It's used in one of the common algorithms called Q-learning that follows this exact principle. It tries to maximize the reward over time. But the problem of using just a matrix is it can represent only a small number of states and small number of actions because it would have to have a huge matrix. So we need something that can generalize it a little bit more. So the answer, obviously, is to use a deep reinforcement learning. The agent's representation of the environment and the behavior is not a matrix, but it's a deep neural network. And that's exactly the case we're trying to solve, our distributed system problem. Because it's a very complex problem that requires hierarchical planning and actions. Sometimes the system has to sacrifice the short-term reward in an attempt to maximize the reward over time. A good example is if the system decides to scale up at a couple of machines, it sacrifices the short-term reward because the system now costs more money. But if the users actually arrive after a period of time, it maximizes its reward because it can handle the load. So it sacrifices the short-term reward in an attempt to maximize the reward in the long run. So I created this gym. In OpenAI, they call gym the concept of a playground. They implemented playgrounds or gyms for many of the typical board game problems that allow people to actually build their machine learning agents and try to solve those gyms. So I created a gym that represents a very simple, trivial example of this distributed system problem. We have a state. The state only consists of a couple of variables. So the concurrent user load that changes over time. Start with 10,000 users, then 12, then 20,000 users. And we have a state of the system. So it has a number of nodes and instance sizes. So 1, 1, 2 means we have 2 small nodes and 1 node that is actually a little bit bigger instance so it can handle more users. The actions we can take in our simplified gym is either do nothing or increase the instance size, decrease an instance size, or add more nodes or remove nodes from the cluster. And the reward we receive is the number of errors. So each node can handle a certain amount of users. And if the system cannot handle all the users that are currently available or currently using the system, then the reward decreases. And obviously, we need to use cost also as part of the reward, because if we didn't, the system or the agent would just learn it would just keep adding nodes and more nodes, because obviously that would yield the highest reward. So we need to include cost, because adding nodes is expensive, and therefore the agent should not really do it. So the agent should be able to find the perfect balance between the number of errors, so handling all the available users, and the cost. So let's look at the implementation in TensorFlow again. Here we have the cost computation. This is the implementation of the gym itself. The cost is calculated based on the number of instances we have in the cluster, and the error is then computed based on both the cost and the ability to handle the current load. And the other interesting function in the gym is called step. So step is essentially taking a step further in the environment, making an action. So based on the action, the environment changes. And also, we compute the cost. And based on that cost, we calculate that reward. And we feed that reward back to that agent. And the agent itself here is represented by really just a simple matrix representation. So similarly to previously, we have the inputs, and then W is a matrix of numbers. And it produces a set of Q values, and the set of Q values is, in our case, just a vector of 5 values representing each of the possible actions, and we pick the highest of those output numbers. And that gives us it tells us which action we should actually perform given that state of the environment. And similarly to previously, when using supervised learning, we have to calculate some sort of loss function. So we tell the agent, or the algorithm, what was the difference between the expected and the actual reward, and we feed that to the agent, and it can improve its internal representation of the environment and then perform better and better over time. And as usual, we just run this in many iterations. Here they're called episodes, and each episode is a run of the distributed system over a period of time. So we just do this in iterations, and essentially we take an action in that environment, receive the reward. Sometimes the agent takes a random action, because we don't want the agent to always try to take the best action, because it could really quickly converge to just always doing the same action. So sometimes we just pick randomly, so it tries different things as well. You can also feed the agent with a history of the load. So if you give the agent just the current load, like 10,000 users, it really does not know how it's evolving. But if you give it a history of last 5 or 10 loads, it may be able to infer some knowledge from that and be able to predict the load in the future. Yeah. So the agent takes a step, picks the best, or receives the reward, and uses the Bellman equation. Again, you can see that TensorFlow representation is actually really very similar to the mathematical representation, and just does this iteratively to improve its internal representation and eventually learns how the system behaves. This is an example of Super Mario reinforcement learning agent. It does exactly the same thing. So it learns by doing actions, but you can see it first jumps randomly for a period of time. It really has no clue what it's doing. Then decides to go to the right because going to the right probably is a good idea. But it runs into the first enemy and just dies. And it can keep doing this for hours and hours until it eventually learns that jumping over the enemy is probably a good idea. So it will learn to do that and will keep doing that, and because that yields the highest reward. So we definitely don't want our distributed system agent deployed to production to fail like this. We don't want to crash our whole system because the agent is trying to learn how it behaves. So we need to set some boundaries. We need to set some very intelligent learning algorithms. There are some really interesting options we can take to avoid these spectacular repeated failures. But eventually, the agent learns how to behave in that environment really efficiently. Here you can see it actually performs really well. It performs probably as a human or even much better than a human, and it can reach the end of the level without any issues and actually really, really quickly. And the goal of our distributed system optimization of our reinforcement learning agent is exactly the same: to learn how to represent that environment and with all of its complexities and the hierarchical planning and the temporal reward, and maximize the reward of the system over time. So that we are the ones setting the reward. So we can value either cost or we can value performance. But we can set that up very intelligently and then use approach like this to find the optimal combination of all our parameters and take actions in our system to optimize that. So in conclusion, still do all the good things when building your distributed systems. You optimize your code, optimize your architecture, do all the good things like define the right consistency for your job, make sure it's there, run chaos tests, define the right delivery guarantees and make sure that you actually have them implemented. Same for reliability and failover, and all the good things that you normally do in large-scale distributed systems. But at the same time, measure what the system is doing, gather data about the system. And if you have the data, you can use the data to improve the system in certain direction. You don't have to build a reinforcement learning agent. But even just looking at the data and trying to optimize and measure the data after your changes is really useful, because it allows you to optimize the system in the direction that you're actually interested in. Thank you very much. Are there any questions? If you have a question, please use the microphone.
I had a question about when you said that it's very difficult to gather data in terms of the kind of inputs you would have for your own classification or regression problem of optimizing so that you get the best performance.
Yeah.
And you said that sort of reinforcement learning can use lesser amount of data and still do the job. So how do you decide what are the kind of actions that should be rewarded and what are the kind of loss functions or cost functions that you use?
Yep.
That would be one. And another being that could there be multiple cost functions with respect to, let's say, you're just trying to optimize the performance of a particular job, but like you said, different jobs could have different kind of performances. So how do you handle that? Do you have an ensemble of algorithms, or is there a one-size-fits-all solution?
No, you can definitely have different cost functions depending on what you're trying to solve, because the way you define the cost function and the reward really it really impacts, that's the main impact of how the agent learns. So the example I presented, if you don't include the cost in the cost function or the reward, the agent will just learn to keep adding more machines. So you have to define that very carefully. And that sort of transitions to your other question, how do you do that? How do you define the, that function? And that's really the most difficult problem that you have to solve, especially in complex problems like this. In some of these gyms, it's really simple because you're solving a simple problem, but in the complex hierarchical system, you really have to spend some time thinking and trying different approaches. And the other difficult problem is, as you mentioned, with the data, because even the reinforcement learning agent has to continue learning for a period of time. So the Google's Go learning agent trains more quickly than any supervised learning algorithm, but still it has to learn for days. It has to, usually, I think it took probably around 40 days to train that algorithm to be able to be the best Go players in the world. So there are approaches how you can start it up. You can give it some like initial knowledge and approaches to avoid failing repeatedly. But still, it's a really difficult problem to solve.
And also considering that the amount of inputs that you're giving is way lesser than the parameters the weights that you will learn in your deep network.
Yeah.
I mean, this distance is a lot more than any image classification, any kind of a problem. So how do you avoid overfitting in that scenario?
How do you avoid, sorry?
Overfitting.
Overfitting?
Yeah.
There's, again, a lot of ways how you can try to do it. One of the ways was even in this super simple example, which is trying random actions once in a while. So yeah, that's there's a lot of interesting ways. Like this was the by far like very simple example that actually does not solve any of these problems. But yeah, that's the core of the problem is using this approach to a large scale system. So this was just really an example. But all of these problems you mentioned are the difficult problems we have to solve. There are solutions, there are ways how to do it, but yeah, it's a difficult problem still.
Thank you.
Okay, thank you. I'll be around for the rest of the day, so if you have any more questions.